Okay, class, welcome back. We are jumping right into electron configurations, so let's get started. Okay, so what is an electron configuration? It is how electrons occupy orbitals. So we're going to use all the information that we learned from the last slides about the principal quantum number, subshells, orbitals, all that stuff, and we're going to take that information and we're going to start writing electron configurations. So an electron configuration shows the occupation of orbitals by electrons for a particular atom. The ground state electron configuration, first of all, ground state is the lowest energy state. Okay, so the ground state electron configuration for the hydrogen atom is as follows. Okay, first of all, we know that the hydrogen atom has one electron. Okay, we also know that the lowest energy principal quantum number is 1. And we also know that the principal quantum number, or the shell, right, n equals 1 shell, can only have an s or subshell. And we also know that the s subshell only has an s orbital, just a single s orbital. So the way that we would write the electron configuration for hydrogen would be 1s superscript 1, indicating that there is one electron in that 1s orbital. So the electron configuration tells us, again, that hydrogen's single electron is in the 1s orbital. That's how we would read that electron configuration. We can also express the same information in a different way. These are called orbital diagrams. So the only difference between an orbital diagram and electron configuration is how the information is presented. An orbital diagram for a hydrogen atom would just be like this. You would write 1s under a box, okay, so that box represents the 1s orbital, and then you have an arrow pointing up, indicating that there is one electron in the 1s orbital. So why did I make this arrow, or why is this arrow pointing up? Why are electrons represented as arrows? And that has a lot to do, or has everything to do with the fact that electrons have this property called spin, okay? And because electrons are like tiny magnets, all right, they spin in essentially two directions. And these directions we call spin up, and we represent spin up by an arrow pointing up. So this is a full, on the left of the screen, this is a full arrow pointing up, but you can see on the right of the screen, we have, sometimes electrons are represented as half arrows. Both of them are correct, okay? So when an arrow or a half arrow is pointing up in an orbital diagram, that's indicating that electron is spin up. And likewise, if we have an arrow pointing down, that means that that electron is spin down. So you have two spins, spin up and spin down. So this feature is a really, the reason why we write it like this is because of the Pauli or Pauling exclusion principle. Same thing, right? Pauli or Pauling. And basically that states that orbitals may hold no more than 2 electrons. Again, we already know this, but they may hold no more than 2 electrons, and the electrons must have opposite spins. And that is essentially because electrons are negatively charged, and we also know that negatively charged particles repel each other. So if electrons are being forced to occupy, 2 electrons are being forced to occupy a single orbital, they're going to be pointed in opposite directions because they're going to repel each other. It's kind of intuitive. So whether or not you represent it as a full arrow or a half arrow doesn't matter, but you need to know that an arrow pointing up is spin up, arrow pointing down is spin down, and when you put 2 electrons in the same orbital, they have to have opposite spins. Okay, So this is kind of, there's actually a lot of information on this slide, but I want you to, first of all, notice that I have ground state up here. So all electrons of an atom in their lowest possible energy state, or their resting state, is called the ground state. Anything else is excited states, okay? So when we're representing these orbital diagrams or these electron configurations, we are doing this as if the atoms are in their ground state. Okay, so on the right side of the screen, I have an orbital diagram that essentially stops at the 5s, all right? We have an energy axis on the y-axis to indicate that the stacking order of the orbitals and subshells that I have are stacked according essentially to energy. The lowest energy orbital is the 1s orbital. We jump up to the n equals 2. We have a 2s and a 2p. There's no 2d, right? We jump up to the n equals 3 shell. We have a 3s, 3 p orbitals within a p subshell, and then 5 d orbitals within a d subshell. Again, we jump up to the n equals 4, and we have a 4s, 4p, and that should say 4d. Sorry about that. I'll fix that in a second. And then we stop at the 5s. Now, the big take-home message for this diagram on the right is that, first of all, each s subshell has a 1s orbital, or has a single s orbital. Each p subshell has 3 p orbitals within it, and each d subshell has 5 d orbitals within it. That's the first thing. The second thing that I want you to see and notice is that the 3d subshell is higher in energy, even though it's slight, but it's higher in energy than the 4s. Okay? It's higher in energy than the 4s. Likewise, that 5s subshell is lower in energy than the purple D. I'm saying purple D because this is a typo on this page, but since I'm live recording, I'll have to fix it later. It's fixed in the other slides. But the purple D subshell should be 4D. Anyway, the 5s is lower than the 4D, or the purple subshell. That's going to matter when we are writing electron configurations, okay? So on the left, I have 1s1, that's the electron configuration for the hydrogen atom, and then I have on the right a single electron pointing up. Okay, so we jump over to the atom that has 2 electrons in its ground state, and that's helium. So you'll notice here that the rule is essentially that I have to fill lower energy orbitals before I fill any higher energy orbitals. So I'm going to place the second electron spin down, and I'm going to fill the 1s orbital. Okay, and then you'll also notice to the left I have the electron configuration of it as 1s subscript 2. Lithium with 3 electrons, we're going to have 1s2, so the 2 electrons are still in the 1s orbital. Now we have the third electron, so we're going to put that in the 2s orbital. All right, so here I have it indicated as spin up. It's just good practice if you only, the first electron that you put in an orbital, you put as spin up, but if you put it as spin down, that's not a huge problem. But when we write the electron configuration, it's going to be 1s2, 2s1. And just so you can kind of see what's going on with the lithium atom, all right, so we have on the left-hand side, I have a picture drawn of a very simplistic picture of the lithium atom. You'll notice in the center I have a +3. That's indicating that lithium has 3 protons. And the first shell, the n equals 1 shell, can only hold 2 electrons because the n equals 1 shell only has a 1s orbital. So there are 2 electrons in the n equals 1 shell, represented by 2 blue dots. And then the second shell, the outer shell, is the n equals 2 shell, all right, with 1 electron in it. And that 1 electron is specifically in the 2s orbital. So again, the electron configuration for lithium is 1s2, 2s1. Beryllium, okay, we have 4 electrons in beryllium, right? So we know that the first 2 are going to go in the 1s subshell, or the 1s shell, or the 1s orbital, right? The second 2 electrons are going to go again in the 2s orbital. We can't put that second electron in 2p. We have to fill the s orbital first, and we're going to do that spin down because the first one was spin up. So its electron configuration is going to be 1s2, 2s2. Boron, 5 electrons, okay? So again, we're going to fill, 1s is filled, 2s is filled. Now the only place to go for the 5th electron has to be the p sublevel or the p subshell. So you'll see here, I have, so 1s is filled, 2s is now filled, and that 5th one is going to go in the 2p subshell for electron configuration of 1s2, 2s2, 2p1. All right, carbon. Carbon has 6 electrons. So again, it's the first 5 electrons are essentially going to look the exact same as they did for boron, right? 2 are going to go in the 1s, 2 are going to go in the 2s, 1 is going to go spin up in a 2p. Now here's the other big thing. This is Hund's rule, okay? Hund's rule is essentially we have to half fill all orbitals in a subshell before we completely fill them, all right? So the electrons in the p subshell stay unpaired as much as possible. That's essentially Hund's rule. So we have to half fill the orbitals, right? We have to keep the electrons unpaired before we pair them up in specific orbitals. And that should intuitively make sense to you, right? Because electrons repel each other. They really don't necessarily want to share the same orbital. So if there are empty orbitals that have the same energy, there are empty orbitals within the same subshell. If there's space, they're just going to go ahead and take their own room, right? They're not going to bunk up with somebody if there's a whole other room available. Okay, so its electron configuration is still going to be, or not still, it's going to be 1s2, 2s2, 2p2. So I'm just going to go ahead and talk about Hund's rule again really fast. Electron-electron repulsions force the 2p electrons to occupy the p orbitals singly, right, rather than pairing them up into one orbital. Right? And they can do that because those 3 2p orbitals are all at the same energy. So this is Hund's rule. When filling orbitals of equal energy, electrons fill them singly with electrons first with parallel spins. So I have, for the first 2p orbital, I have a spin up, and the second 2p orbital, I also have spin up. All right, so oxygen, 8 electrons. All right, so here we go. That's 2 more electrons than carbon. Okay, so again, it's going to look the exact same. The 1s is filled, the 2s is filled. We originally had one in the 2p and the other one in the second 2p. Now we have 2 more electrons to fill up. We're going to put the third one in the last remaining empty 2p, and then the final electron we have to pair it with within one of the orbitals. So I just went ahead and just put it on the far left, but the big key is you put it spin down, okay? So when we put 2 electrons in an orbital, they have to be opposite spin. So oxygen's electron configuration, 1s2, 2s2, 2p4, because there are 4 electrons in the 2p subshell. So let's try argon. All right, and I'll give you a second it's probably a good idea. I would go ahead and pause it right now. Go ahead and try argon for yourself. You can do the electron configuration as well as the orbital diagram. And I'll go ahead and wait, but I'm not going to wait too long. You should just pause it. Okay, so I'm assuming that you paused it right now, and now we're going to go ahead and start. So argon, if you look at the periodic table, argon has 18 electrons. So since argon has 18 electrons, the first n equals 1 is completely filled, n equals 2 is completely filled, and you will notice that n equals 3, 3s2, 3p6. So our electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So I'm going back to the ordering of the energy of the ordering of the orbitals because of their energy. All right. So in multi-electron atoms, right, basically everything besides hydrogen, the subshells within a principal shell do not have the same energy because of electron-electron interactions. And I've already stated this to you earlier. The 4s orbital is lower in energy than the 3d. Okay, so not all of the subshells within the n equals 3 shell are equal energy. Different subshells within the same principal shell have different energies. Again, the 4s subshell is lower in energy than the 3d subshell, even though its principal quantum number is higher. Okay, so we have to take that into consideration when we are filling electrons. Okay, so essentially after 18 electrons, all right, so let's say we want to make an electron configuration for, that was argon, we want to go to, hopefully you're looking at your periodic table at this point, potassium, all right, that's an n equals 4, okay, so potassium, remember potassium, if you look at the periodic table, potassium is actually in the n equals 4 subshell. Shell. That's how you can look at it because it's in the 4th row of the periodic table. So we already know that argon has 18 electrons, so potassium has 19. So where are we going to put that 19th electron? Are we going to put it in the 3d subshell, or are we going to put it in the 4s? Now, two things. One, because the 4s is lower in energy than the 3d, we're going to put it in the 4s. The 4s levels get filled before the 3d levels do because the 4s orbital is lower in energy. So we're going to put that last electron, that 19th electron, in the 4s shell, 4s orbital, not the 3d. And this thought process actually makes sense if you look at the periodic table because potassium is in the 4th row. So that 19th electron is going to be in the 4s orbital. Okay. It should also make sense to you, remember when we were talking about how the first column, okay, the first column of metals, those guys always like to be a +1. They always give up electrons, and they always give up 1 electron. This is why. It wants to get to a noble gas configuration core of argon, which is 19 electrons. So a lot of times when potassium, every time, when potassium reacts with anything, it's going to give that 1 red electron to get to a stable noble gas core configuration and of its closest noble gas, to it, which is argon. Okay. So again, potassium's electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, 4s1. So you might want to ask yourself, or you might be asking yourself, well, when do we fill the 3d subshell? Well, you can even look at this energy diagram or orbital diagram on the right, and you can answer that question for yourself. If we fill the orbitals according to their energy, calcium, right, the electron configuration for calcium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay. Then we go one element over, okay, to scandium. Now, scandium is going to have, it's going to be the same electron configuration as calcium, right, with one more electron. So where is that electron going to go? That electron is going to go in the 3D because the 4p is higher in energy than the 3D. Okay, so I went ahead and did a zinc for you so you could get a better feel for filling this 3D subshell before you fill the 4p. If you look at the periodic table, zinc is number 30. That means it has 30 electrons associated with it, okay? It's also in the fourth row, all right? So it's going to be in the fourth row. And in the fourth row specifically, it is 12 blocks over. So essentially, everything that's n equals 3, so we're going to have the 1s2, 2s2, 2p6, right? 3s2, 3p6, all right? That brings us essentially up to 18 electrons. Then we jump down to the n equals 4, and we're going to have 12 electrons total, all right? 2 of those electrons are going to go in the 4s2. That leaves us with 10 remaining electrons, and all 10 of those are going to go in the 3D subshell, completely filled, all right? And we don't start filling the 4p until we get to gallium, which is 31 electrons, okay? So zinc's electron configuration, again, I want you to notice that we fill the 3D, we fill the 4s first and then the 3D, okay? So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, okay? So just to make sure you understand the ordering really fast, we're going to start off here at 1s, all right, and we're going to follow the arrow. So we fill 1s, then 2s, then 2p, then 3s, then 3p, 4s, then 3d, 4p, 5s, 4d, 5p, 6s, follow the arrow, 4f, 5d, 6p, 7s, 5f, 6d, okay? So whether or not you need to commit this to memory, that's fine, but you have to know how to fill orbitals correctly and in the correct order, all right? So everything's at business as usual up until 3p, all right? But after 3p, we fill the 4s, and then we fill the 3d, okay? So 4s, 3d, 4p, 5s, 4d, 5p. And then we don't actually start filling f orbitals until 6s, all right? And if you look at the periodic table, if we look at the 6th row, all right, that's where the lanthanides and actinides come in, okay? So that's why we actually have that 4f subshell for all those electrons that are in there, okay? So commit this to memory, and you're going to really need to know it for when you actually start writing electron configurations. All right, so recap. When we write electron configurations, lower energy orbitals are always filled first. Orbitals can only hold 2 electrons, and they must have opposite spins. This is Pauling's exclusion principle or Pauli exclusion principle. And then when orbitals of identical energy, all right, so orbitals within a subshell, so the 3 orbitals within a p subshell, the 5 orbitals within a d, the 7 orbitals within an f subshell. When you're filling these orbitals, you have to first singly occupy each orbital within a subshell with parallel spins. Then you go back and pair the spins if you have to. All right, this is known as Hund's rule. All right, so now that we talked about electron configuration, it's important for us to understand valence shell and valence electrons. So all the electrons in highest energy levels of an atom are also the furthest away from the nucleus. Now, since they're furthest away from the nucleus, that means they're the most reactive. Because if you think about it, the only thing holding those electrons there is the electrostatic interaction, the positive charge of the nucleus, right? So if the electrons are far away from the nucleus, they're going to be held less tightly, less securely than electrons that are closer to the nucleus, all right? So these electrons that are furthest away, they are called valence electrons, and they are within what we call the valence shell. Valence electrons, again, are the most reactive. They're involved in all the chemical bonds, forming, electron transfer, all that stuff. We always look at valence electrons because those are the electrons that are the most reactive, okay? So if we look at lithium for an example, we can see that lithium has essentially two kinds of electrons, right? It has three collectively, but two of those electrons are in a core shell, right? That's the 1s shell, n equals 1. And the highest energy electron is that single electron that's in the 2s orbital. So we can sit back and say that that 2s1 electron is lithium's valence electron. All right, and we'll talk a little bit more about that later, but let's look at valence electrons again, just to make sure that you understand. So electrons with the highest energy level numbers of an atom, so the electrons with the highest principal quantum number are its valence electrons. And the electron configuration tells us how many electrons are in the valence shell. So if we look at silicon, all right, so everybody hopefully please look at your periodic table. Silicon has 14 electrons total, okay? Silicon is in the third row of the periodic table, okay? And you can even count across. Silicon has 2 electrons in the n equals 1. It has 1, 2, 3, 4, 5, 6, 7, 8 electrons in the n equals 2. So that's the 2s2, 2p6. And then we jump down to the third row. Silicon is 4 squares over. So that means that silicon has 4 electrons in its valence shell. All right. Those electrons are specifically 3s2 and 3p2. All right. So those are the valence electrons. I have them highlighted in yellow here. So you can look at it that way, okay, where all the electrons in the highest principal quantum number shell, those are the valence electrons. Those happen to be everything in the 3s2 and 3p2. And everything below that in the n equals 1 and n equals 2 shells, those are the core electrons of silicon. Now let's jump one. Let's go to selenium. Selenium is a little bit more complicated, right? Selenium has 34 valence electrons. All right. So we know that its electron configuration is here: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. All right. But because, now if I asked you what are selenium's valence electrons, you would have to know that this is the correct order of the electron configurations, of the electron configuration. And you would have to just essentially look at the fact that, or ask yourself, what are the electrons in the highest principal quantum number shell? First of all, the highest principal quantum number shell is 4. Okay, so everything in the 4s and 4p are valence electrons. Even though the 3d10, even though those electrons get filled, after the 4s2, because it has a principal quantum number of 3, it technically is still considered a part of the core electrons. So it's a little bit counterintuitive, but so when we look at valence electrons, we're just going to have to look at the fact that we only look at the electrons that are in the highest principal quantum number. So all other electrons, including those in the 3D orbitals, are core electrons. So the electrons with the highest energy level numbers of an atom make up its valence, and the electron configuration tells us how many electrons are in the valence shell. All right. So if we look at oxygen really fast, oxygen 1s2, 2s2, 2p4, it has 6 valence. The 6 valence electrons are in the n equals 2 shell. Beryllium, okay, 1s2, 2s2, it has 2 valence. The 2 valence come from the 2s shell. Zinc, now here's zinc. Zinc has 2 valence electrons only. And that is because only 2 electrons are in the principal quantum number 4 shell, okay? So electron configurations in the periodic table. All right, so we can actually we can see some kind of pattern from the periodic table when we are looking at valence electrons. The elements within a column, so elements within a column of the periodic table, all have the same number of valence electrons and similar outer electron configurations. All right, and that is essentially why all the first row metals form +1 ions. It's because they all have 1 valence electron. So you'll notice lithium and sodium, they all have a 1 valence electron. For lithium, it's the 1 electron in the 2s. For sodium, it's the 1 electron in the 3s. Beryllium and magnesium, second column, they all have 2 valence electrons. We skip over to group 3a, all right? Boron and aluminum, they all have the same number of valence electrons. Boron has 3, aluminum has 3. The only difference is that boron has a 2s2, 2p1, while aluminum is 3s2, 3p1. Let me go back. We can just jump over to the halogens, fluorine and chlorine, right? They all have the same 7 valence electrons, same 7. All right. The only difference is that fluorine has n equals 2, so that it has 7 electrons in the n equals 2 shell, while chlorine has 7 electrons, of course, in the n equals 3. If we jump over to the noble gases, you will notice one big thing. Their valence shells are filled, right? The 2s2, 2p6 for neon can't have any more electrons in there. They have a completely filled valence. Argon, same thing. 3s2, 3p6. That is a completely filled valence shell. That is why the noble gases essentially don't react with anything. They have a filled valence. All right. Fluorine and chlorine only need 1 more electron to get to a filled valence. But if we go over to lithium and sodium, they only need to get rid of 1 electron to have a full valence. Okay, so this is a preview to why atoms form certain ions, why lithium and sodium form a +1, and why fluorine and chlorine always form a -1. So a recap really fast. Valence electrons are the electrons in the outermost principal shell, the principal shell with the highest principal quantum number n, and these electrons are very important because they are involved in chemical bonding, and electrons that are not in the outermost principal shell are called core electrons.